Okay, first of all, good morning. This is going to be our presentation, our paper presentation. This is a great day for us because this presentation is going to be the conclusion of this hard work we have done. So um, let's get started. Luciano is going to start with the introduction of this project about the water consumption reduction with an electronically controlled drip irrigation system.
Okay, good morning. We started talking about specifically of the water crisis and its impact on health and the environment. And we continue talking about an engineering contribution for the society. Continuing with the next slide. Yes, an engineering contribution, and continue with the next slide. We have the basic aspects about the water crisis. It is a well-known fact that the world is facing a big crisis related to the water crisis and its scarcity. We know that the water systems are very stressed in around the world, and we have to understand the right of the water to our lives. Here we have a few pictures about the water crisis, but specifically in the picture of the world in the map, we can see the water stress by country for 2040. It is in a projection, and we can see that it is notoriously severe. And this is why we must take action on this problematic. Now, continue Jerónimo with the basic aspects.
So when we talk about the water crisis, we have to understand what the water scarcity is. Most of the people tend to think they are same, but we have to understand that the water scarcity is actually one of the causes of the water crisis. And this is a wide problem. The water scarcity is also caused by other causes, and one of the main causes is the availability. And we have to understand, we can understand availability, sorry, from seeing this picture at the bottom, because people who is not aware of the water crisis or water scarcity may think that why is this a problem if the planet Earth is covered by water? And in fact, that's true. The water covers 70% of the surface of the planet, but 97% of that water belongs to oceans, and that is salty water that is it cannot be consumed by humans or animals. And just the remaining 3% is fresh water, what in Spanish we call agua dulce. As I made this much just for understand. But from this 3% of fresh water, 70% is frozen, is in glaciers or in the poles. 29% is underground, is water that must be pumped, and then it needs some treatment, some filtration and chemical treatment in order to make it in order to make it also the solution for human water consumption, and the remaining 1%, actually less than 1%, is in lakes and rivers. And this water is easier to get access to, but it also needs some treatment. So from this picture, from understanding these statistics or these figures, it is easy to understand that those countries or areas around the world have not access to lakes or rivers will need an extra job to get that fresh water. And here is where we come with the other problematic, which is the access to this water. And it can be caused by an irregular supply, which happens, for example, when the government wants to control this the water consumption, and this can be especially seen in dictatorships. And the other problem is about the infrastructure. If those countries don't have an special infrastructure in order to get that water, for example, water which is underground or frozen water, or even salty water coming from oceans, we must go through a desalination process. Those countries will not have a proper access to fresh water. So water scarcity is a wide problem. It's not just about water availability, and it is one of the main causes of the water crisis. So it is our responsibility as part of society, of course, but also as engineering students to come up with solutions. And in order to state a possible solution, we have developed this investigation about one, not solution, but a contribution, because it is known from the United Nations, some United Nations statistics, that 70% of water consumption every year is caused by agricultural processes. So we have developed this investigation about a system, a drip irrigation system that can help to reduce that consumption. And in order to introduce you to this system, we are going to follow these sections. First of all, the definition in which Luciano is going to introduce you to this system. Then we'll go through the advantages and disadvantages and for the system. We have divided them in three main categories, which are the water and soil issues, where we will see how this system works with the water, how it can help to saving water, and how it affects the soil. Then about those issues related to cropping and cultural practices, which are related to how the system works, or how the farmer, for example, how to make this system work with the crop as a whole. And finally, the system, about the system infrastructure, where we can see how this system can be developed. Then the remaining three sections will be about the design of this system. First of all, we'll see which soil and environmental parameters are involved. And then we'll see some electronic characteristics that we can make use of in order to turn this system into a smart system. And finally, we'll see the system architecture. First, the automation section or the electronic unit assembly, and finally the general system assembly.
Okay. Now addressing the definition of the system, subsurface drip irrigation system is based on the application of water, of course, in a slow and localized way to the plant. Basically, the composition of the system consists in tubes around the plant, and these tubes have a regulated water drip. Next, the development of the system has some advantages and disadvantages that we are going to talk in the next slide. Now, starting with the advantages, we can see more efficient water use, and this is because the system uses unlocalized irrigation. We can see that in the next, we can see that less water quality hazards and enhanced plant growth. And this is because we can have a specific control of the water use, and this is why we can see too an improved fertilizer and better weed control. Now continue Jerónimo with the disadvantages of the system.
Okay, about the disadvantages, one of the main disadvantages related to the water and soil issues is the small wetting pattern on coarse texture soils. And we can see this this kind of soil, this coarse texture soil in the lower right picture there. And this is because in this kind of soils, it is easier to the water to move through the pores of this type of soil, and it occurs a process which is called percolation, and this is a process by that in which the water tend to sink through the pores of the soil, and it reduces the wetting pattern around the roots of the plant, because as I say, the water tend to move downwards. Then another disadvantage is the monitoring and evaluation irrigation events, and this is because the drippers and the drip lines are varied, are underground, so it's more difficult to keep control over how the water is being applied to the root zone, or even if a dripper is clogged, it is difficult to detect it. Then we have the meter discharge rate. This is because if a meter has a fast discharge rate, this is that the water comes out too fast. In some kind of soil, it will be difficult to the water or to the soil to redistribute that water, and it can occur that too much water stays in the root zone, and we know that is not good for the plants. They need if possible, an equal input rate and output rate of that water. Then the location and positioning of the drip lines, sorry. This is because if the drip lines are near the surface, the trillage options can be reduced, and it can hinder the possibilities of using some machinery to develop the trillage process. Then we have restricted plant root development, because it can occur if the drip lines are near the root of the plant or the stems of the plant. The plant itself cannot have enough and a wide area to develop their roots, and it is one of the main parts of the plant because from the root the plant takes the nutrients from the soil. So if it cannot develop a wide root zone, maybe the growth of the plant or of the crop can be reduced. And finally, the infrastructure cost, and this is a system that needs high investment for being developed, and it has the estimated life for this system is shorter than traditional system, for example, but it is estimated that it can remain operative for 10 to 20 years. So in order to help with this, it is necessary to increase the production and the production of the crop or the crop yields in order to make it possible in the future to invest in maintenance or in a whole system replacement. So we need to get some characteristics of the soil in order to design the system. We are going to focus on the automotion of the system, not in the drip lines or drippers or tanks, because it is not the aim of this paper. We want to introduce the electronic characteristics that we can apply to the system. So first of all, we need to know how much water we need to apply to the crop. And one of the most used methods to do this is known by water balance method, which make use of an equation which relates the water inputs and water outputs, and it tries to balance them. In this picture, we can see that okay, we need to know which are water inputs and which are water outputs. In the picture, we can see from the arrows that precipitation, for example, is one of the water inputs. It's actually one of the main water inputs, and the other one, in our case or investigation, the most important is the irrigation. It's the water that comes from irrigation. And the main water output occurs by a process called evapotranspiration, which is the sum of two sub-processes, which are transpiration and evaporation. Both occurs when the water in the crop or in the field leave the zone or the plants as vapor, as steam, And in the case of evaporation, it happens when the water which is in the soil surface evaporates, and for transpiration, it occurs to the water which is on the stems or on the leaves of the plant. So in order to determine this water output as evapotranspiration, we need to know that there are many parameters that can affect this evapotranspiration, and it can be also be determined. And if we keep track of these parameters that can affect the evapotranspiration, we can get an estimation from this equation. And finally, we can apply the water balance method in order to know how much water we need to apply to the crop. So, as we can see there, we have the water balance equations. It relates those parameters we have seen. I and R represents irrigation and rainfall. ET sub C represents the evapotranspiration for the crop that we are studying. P is percolation, is the process that we have explained earlier when the water moves through the pores of the soil. S represents seepage or filtration of the water in or out the root area. In this case, is out the root area, the root zone. R sub off is runoff. Is the water that moves through the surface, and D sub W is the change in the water content of the soil during the time period that we are studying. So many of these parameters are difficult to measure, or they cannot be electronically measured. So for this system, we can just make use of 3 of them. So we have the simplified version of this equation, which represents that the irrigation, this is a balance, and represents that irrigation water, the amount of the water coming from irrigation, must equals the water that is leaving the crop by evapotranspiration minus the water that comes that comes to the crop as rainfall. So the evapotranspiration can be determined, as we can see there, as Kc times Et sub 0. Et sub 0 is the reference evapotranspiration, and it depends in many conditions. Mainly depends or is affected by weather conditions or by environmental conditions as solar radiation, wind speed, altitude, air temperature, and relative humidity. And those are all parameters that we can measure by using sensors. And K sub C, sorry, is the crop coefficient. It is a dimensionless number, and it affects the reference evapotranspiration to the crop that we are studying. And this value can be taken from charts, from tables, as we can see there, and the chart at in the right comes from some areas in India. We can see, for example, that there we have some crops at different locations, and we can say, for example, that for Paradip, which is a region in India, the tomato crop coefficient in January is 0.6, and that is the value that we need to apply to that equation in order to modify the reference evapotranspiration. And it can also be, it can also change according to the crop development time season. This is depending on which time of season we are. This value can also change. So, in order to measure though that reference evapotranspiration, we need to make use of an electronic system. And now Luciano is going to explain how we can do this.
Yes. Now, okay, in order to talk about electronic characteristics and system architecture, we must know about types of microcontrollers, and we must know too about components and sensors. And next this, we will can understand the system description and its functions. Now, in the next slide, we can see some types of microcontrollers. In our case, we use the platform Arduino. Here we can see the most commercialized, like Arduino Nano, Arduino Mega, Leonardo, Uno, y Arduino Jun. Arduino basically is a very used microcontroller within electronics. Arduino works with open source platform and with open source libraries. And we can see too another microcontroller like Raspberry Pi, but for our system we use Arduino. Now, Jerónimo continue with a few types of sensors for our system.
Yes, so as I told you before, we need to measure some environmental and soil characteristics in order to keep track of the reference evapotranspiration, and from this we can estimate the crop evapotranspiration, and finally we can know how much water it is necessary to apply to the crop. So in order to do this, we need to use soil moisture sensors. One of the most used versions is the SparkFun soil moisture sensor that we can see there in the picture. And it makes use of those two paths which need to be buried in the soil. And it functions, it acts as a variable resistor, because when the soil has a high moisture content or water content, the current flow from one path to the other is going to be higher than when the soil moisture is low. So we can measure this difference in the current flow in order to determine this the soil moisture content. We have some other sensors as FC28 or a capacitive version, but they are pretty the same and they look the same. Then we need to measure the temperature and relative humidity. And one of the most used versions is the Adafruit BME 280. That it is there in the picture. It is a good option because it is a tiny board. It is 0.7 inches by 0.7 inches, so it can fit almost everywhere. and it also measures barometric pressure. So we can, from all those parameters, we can determine also the altitude. And as we saw in the previous slide about the reference evapotranspiration, that is a parameter that is going to be useful for determining that value. We can also use DHT11 and DHT2022. They are cheaper sensors, and they just measure temperature and relative humidity. And finally, we need to know how much water we are using. This is the aim of this paper is to develop a system to keep control of the water consumption. So we need to measure this, and we are going to use this kind of sensor that we can see there in the picture. It is a flow rate sensor. It is called YFS201, and it works. It goes in line in the main water line, and it has a spinning wheel inside and a Hall effect sensor, which detects when a magnet passes in front of it. So this spinning wheel has a magnet, and because of the water flow, this wheel is spinning, and the magnet, every time the magnet passes in front of the Hall effect sensor, it sends a pulse. So measuring the frequency of this pulse, we can determine how much water is going through the line, because in a way we are measuring the speed of the wheel. So now that we know which kind of sensors we need to use, and the microcontroller that we are going to use, we can develop the electronic unit block diagram. And we start by the Arduino microcontroller in any of its versions. The version will depend on how much inputs or outputs we need to, the project will need, but it will need to be stated in the design stage of the system. So then we have signal conditioning circuits that will help us to connect, or to help the Arduino microcontroller to properly read properly keep or track the sensor readings. And then we have the sensors we have previously seen: soil moisture sensors, environmental condition sensors, and the flow rate sensor. Then we have driver circuits, which help the Arduino microcontroller to control those loads that need more energy, more power. For example, the water pump or the valves, which need to be activated from the electricity coming from the line, from the grid. So the Arduino microcontroller will send a signal to the drivers, and then the drivers will activate the water pump or the valves. We have a communication interface, because, for example, in order to determine the rainfall, that parameter that we have seen that we need to know how much water we need to apply, that information will need to be taken from a weather station or from a weather service, for example. And this communication interface can, for example, if it is based on a Wi-Fi interface, it can help us to connect to a cloud service and take that information from, or it can also be formed by a Bluetooth interface or GSM interface, and that can allow the end user or the farmer, for example, to control the system by using a mobile phone. Then we have the user interface, which can be developed by using a keyboard and a display, and it will help to the user to control some parameters or some, for example, soil moisture thresholds, which will tell the system when it has to activate or not. Or for example, if the soil moisture sensors fail, an irrigation schedule can be programmed, and if those sensors fail, the user can activate this time-based program in order to keep the system working. And now Luciano will present the general system assembly.
Yes. Now, talking about the general system assembly, here in this picture, it is possible to see how the system must be implemented. We start with the water source. Next is connected with the water filter and the water pump. The water pump is connected with the power supply and the electronic unit. The electronic unit, in the electronic unit enter the signal of the environmental sensors, and the electronic unit is connected with valves, soil moisture sensors, and crop row. After the water pump, we can see chemical injection unit, and next the flow rate sensors. And all this set forms the complete system. And finally, in the next slide, some conclusions we reached in the development of this work are first, we can see real-time feedback control systems. This is thanks to power processing of the microcontroller. Second, we can see an effective model for modernizing small and large-scale industries. This is a great point because is very possible the application in the Argentine industry. And finally, we can see an effective water and resources saving. This is a great point. Is the main problem that caused the research and this work. Next, we can see the reference. And this is all of the presentation. Thank you for your attention.
Thank you for your attention.